All right, we're going to continue a little bit with the optimization problems that we did on last lesson. This section should be a little bit more applicable, I guess, to some, as you could say, real-world situations, and that will solve some real-world scenarios and introduce a few more concepts with optimization. Now, the goal in all of these is to either maximize or minimize whatever we're asked to do, whether it's volume or area, or a number of, it could be revenue, it could be anything like that. So the number of possibilities for optimization problems is kind of an endless list. So there's no way we could actually do every single type of problem. What I'm going to do is show you 4 problems. I would like you to write down these 4 problems, and then you're also going to have 4 to do on your own. 3 of them will be really similar, and one of them I want you to just try to kind of figure out on your own. Again, we're gonna do 4 together. You'll have 4. I want you to write down all problems and turn in all problems. So write down and solve all 8. So kind of treat it as if you were in a traditional classroom setting. We go over these example problems. You write down the example problems as we go along, and then you've got an example so you can do it when you go to do it as well. So let's go ahead and get started with the first one. In this scenario, a manufacturer is going to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with the maximum volume? So think of like an Amazon box. They've got this surface area of material, and they want to make a box out of this material that would hold the most, have the most volume, can hold the most stuff, if you will. So let's draw a picture, and that's what I would suggest in all of these, if you don't have a picture, is to draw a picture first. So this box has a square base. Let me just draw a little sketch here. Three-dimensional box. All right, so there's our box. The base, like I said, is square. So let's think about the 2 equations that we have. In your first video, I talked about having like 2 equations. One you can call your constraint equation, and then your other one is what you want to maximize or minimize. So let's look at the 2 equations that we're going to have here. So the first one it talks about is surface area. And then the other one, we want to maximize volume, right? So 2 equations here. You won't always have 2 equations, but in this scenario, there are 2 equations. So we want to maximize the volume, but the surface area we're going to use to eliminate one of the variables in volume. So if I were to label this box, the key thing here is a square base, because a square base tells us that the sides are all equal at this base. So this is the same and this is the same. All of these sides are, we call S. Let's call those sides. And then there would be a height. We don't know the height, so we'll call that H. And if we're talking about the surface area of this box, well, there's really 5 sides. We don't have a top, so we don't have to worry about the top side. But we've got this bottom. So the area of the bottom would be, well, length times width, so that's S times S, so that'd be S squared. For the bottom, plus now we've got 4 sides of this box, and each of these sides have an area of length times width, so S times H, and that's going to be the same for all 4 of these, because it's got a square base, so all of these sides have to be the same. So we'll say 4 times SH, 4SH. So that would represent our surface area. And we know the surface area is 108 square inches, so we could say 108 equals S squared plus 4SH. And then let's take a look over at volume. So volume for any like rectangular prism would be length times width times height, right? Generally, length times width times height. So in this scenario, our length and our width are both S, so it's like S times S. And then our height will just be height. So we've got really S squared H would be volume. And this is what we want to maximize. right? In order to do that, though, we've got to get rid of one of the variables. We've either got to get rid of s or h. So we use this other equation. We could call this our constraint equation to solve for one variable so we can plug it into the other equation. These are kind of similar to related rates, right, where you had to take one equation, solve for a variable so you could replace it in the other one. So in the surface area, the easiest variable to solve for is going to be h because, well, if we did the s, we'd have to like factor out an s and then divide. And well, h is the easiest one here. So to solve for that, we're going to just subtract that s squared over first. So minus s squared equals 4sh, and then just divide by 4s. So then h is equal to 108 minus s squared over 4s. All right, so we could go ahead and plug that into, now we're going to take this and we're going to plug it in for that h. So then we'll end up with v equals s squared times 108 minus s squared over 4s. And now we've got an equation with just one variable, so that's good. Let's just go ahead and simplify this a bit before we differentiate it. So if I just distributed this in, I'm going to kind of look at this as s squared times 108 over 4s minus s squared over 4s. So we can break apart that fraction so long as we just keep the 4s on both of them. So then when we distribute through, simplify this a bit, v would be 108 s squared over 4s minus s to the fourth over 4s, and then reduce those, we get 108 divided by 4 is going to be 27 s minus, and I'm going to write this other one as just 1/4. So like an invisible one there, s to the third. So that's probably the easiest way to then differentiate it. You don't want to leave it as a fraction, like a whole big fraction, because then you'd have to use the quotient rule. All right, so then let's go ahead and differentiate it, because remember, that's how we maximize something, is we take the derivative and set it equal to 0. So let's differentiate and set equal to 0. So we get v prime. You could also call that dv dt, I suppose, if you want. I'm just going to call it v prime. And that's going to be 27 minus 3/4 s squared. We then set that equal to 0 and solve it. So let's just take the 3/4 over 3/4 s squared. If we add that over, equals 27. And then we'll multiply by the reciprocal. So we get s squared equals 36. And we then can take the square root of both sides, and s equals plus and minus 6. So the side length of this is either going to be negative or positive 6. Now the obvious answer is positive 6 because you can't have a side length of negative 6. So s equals 6 inches. Now, there was actually someone asked a question. How do we know if it's a minimum or maximum? It's a good question. The way that you could actually tell, if you want to be 100% certain, would be you could do like our little table where we did like, you look at increasing to decreasing, decreasing to increasing, determine if it's a min or max. I'm just going to make a little number line to kind of show you here. So if we put our two critical points, -6 and +6 on there, and then all we'd have to do is just plug in a number less than -6 into our derivative. So if we did like v prime of -7 and see what we get. So we just plug it in there. And that would give us, let's go ahead and, so if we plug that in, 27 minus 4/3. And you could also plug that into your table times -7 squared. That's going to give you a negative And then if you plug in like v prime of 0, that's going to give you a positive. And then if you plugged in like v prime of positive 7, that's going to give you a negative. So then what you'd have happening is a negative to positive here, so that'd be a min, and then a positive to negative, so it'd be increasing to decreasing, so that'd be a max. So that tells us there's a max at positive 6. There's a minimum at negative 6, but in this scenario, negative 6 doesn't even really exist because you can't have a side length of negative 6. So we do know this is a maximum at s equals 6, right? So in the context of this problem, we're asked to determine what dimensions. So we did find one dimension, the side is 6 inches. However, we do still need to find h, the height. What height is this thing going to be? So we can just go back and use this here. H is 108 minus s squared. So h would equal 108 minus 6 squared over 4 times 6. Solve that. So h equals 108 minus 36 over 24. And that would reduce to 72 over 24. 6 goes into 72. I guess 12 does, so it'd be 6 over, it's 3, I guess, right? Yeah, which equals 3. All right. 3 inches. So we would have a side length of 6 inches and a height of 3 inches. Those would be our dimensions. So 6 inches by 3 inches. Now, if we also wanted to find what that maximum volume was, that would be pretty easy as well. So the max volume would then be, just plug it in here, s squared times h. So it would just be 6 squared times 3. So 36 times 3, which give you 108. So 108 inches cubed. That's how much material we could hold inside this box. All right. So this one, you don't have to do one actually, sorry, you do have to do one like it's number 3 is like number 1. All right. So you'll use number 1 as a reference to solve number 3. Very similar. Now the only difference is on number 3, it's told that it's going to hold 864 cubic feet of water. So it's giving you volume. And then you're going to find the dimensions you want to minimize the surface area, sort of the amount of glass, the surface area of the glass. So it's going to be kind of the opposite. You're going to be given volume. You're going to solve for one of the dimensions. But again, notice it is a square bottom and an open top. So it's going to be sort of the same deal. It's just you're going to be given the opposite one. All right, let's go ahead and look at number 2. Number 2 is a very classic problem that you would see if you just like Googled calculus optimization problems. You would probably see somewhere this square box idea where we're given a piece of cardboard. In this case, it's a 16 inches by 30 inches piece of cardboard. And we're going to create an open box. So now think about if you're creating an open box with this piece of cardboard, what would you have to do? We'd have to somehow like fold up the sides to create a box, right? How you would do that would be you actually would cut a little square out of all 4 corners so that you could fold them up and then the sides would meet. So you'd be cutting out these little squares. So the question is, what size of square should be cut out of each corner to make the box with maximum volume? So should we cut out just like a little 1 inch by 1 inch square and fold it up so this be this, this sort of box like this, right? Or should we cut out a big square so it end up with something like this? So what dimensions are going to maximize our volume? The way we're going to label this is we're going to cut out a little x by x square in each of these. So we're going to call this x by x, right? So we have to figure out what size square that should be. So we're going to change a little bit how we label these sides. If overall it's 30 inches, when I cut that square out, I'm left with just Well, really this length here. So instead of calling that a 30-inch, I'm going to call this 30 minus, now I cut out a length of x here, and I cut out a length of x here. So I'm going to call that 30 minus 2x. And then on this side down here, I'm going to do the same. So that's going to be 16 minus 2x, because I'm cutting out a length of x from each of these. So what I'm left with in here is 16 minus 2 times whatever that x is. So then if we start to write our equations here, well, we've got the area of this cardboard, right? But we want to maximize the volume of it, right? And we're actually going to have just one equation here. When we look at the volume, we can actually write this all in just one variable, because we have, like, for the volume of a box, it would be length times width times height. So if we look at the length of this, well, the length is going to be, we could say here, 16 minus 2x, right? Our width would be this way, right? Those are our two dimensions there, which is 30 minus 2x. And the height of this thing, we don't need to call it h, because the height of this is going to actually be determined by whatever we cut out that x there. Because if we cut out, length x right here and here, right, and we fold it up, that then becomes the height when we fold it up. This becomes the height. So the height is actually just x. So we've already got an equation with just one variable. And so we can go ahead and just reduce this a little bit and then maximize it. You do not have a problem like this to do on your own. This one's going to be unique in that we just do one of these. So I want you to see an example of this. So let's go ahead and multiply this through and see if we can't maximize it. Don't try to differentiate off the bat, because then you're going to have to do two product rules. So you do want to simplify this if you can. So we need to FOIL this first one. 16 times 30 is 480 minus 32x minus 60x, and then plus 4x squared. And then all of this gets multiplied by x. So let's see, we end up with 4x cubed. These two combine to give us 92. So that's going to be minus 92x squared, and then plus 480x. All right, now we can go ahead and differentiate it. It'll be pretty easy now because it's just a polynomial. So v prime then would be 12x squared minus 184x plus 480. So since we've got differentiated one variable, we'll set it equal to 0 and solve it. There is a common factor we can pull out of that, and that is 4. This up here. So if we pull out a 4, we'll have with 3x squared minus 46x plus 120, that equal to 0. We then can just divide out that 4. So we're left with 3x squared minus 46x plus 120 equals 0. All right, now you would want to try to actually factor this. I don't think you're going to have a lot of luck factoring that. In this one, we actually want to use the quadratic formula, which is good because that's a tool that you're supposed to just know for the AP test. So hopefully you have that memorized. Quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac over 2a. So let's go ahead and apply that to this problem. We get x equals 46 plus or minus the square root of negative 46 squared minus 4 times 3 times 120, all over 2 times 3. Let's reduce that. We get inside the parentheses there, negative 46 squared minus 4 times 3 times 120. Get 46 plus or minus the square root of 676 over 6. And the square root of 676 is actually 26. So x equals 46 plus or minus 26 over 6. From this point, a little bit rusty on doing a problem like this, you want to break it apart into x equals 46 plus 26 over 2, or sorry, 6, and then x equals 46 minus 26 over 6. So then we get 72 over 6, I believe, and 20 over 6. So from here, 72 divided by 6, we get 12. And this would just reduce to 10/3. All right, so we do actually have two possibilities here. X equals 12 or x equals 10/3. So we got to figure out which one. Now, again, what you could do is you could do this number line deal, 10/3 and 12. You could then plug in v prime of a number less than that, say like 0. If you plug in v prime of 0, you're going to get a positive. And then do v prime of, say, 5. So we just plug it into v prime up there. And we will get, I believe, a negative. Just double check. Yep, we get a negative. And then if we did like v prime of 13, we'll get a positive. So what we would have happen there would be increasing to decreasing, decreasing to increasing. So we're asked to find we want to maximize the volume, right? Largest volume. So we obviously want this one 10/3. That would maximize it. This would be a minimum, right? And this would be a max. Now, you wouldn't actually have to do this as well in this case because we can actually eliminate x equals 12 from the outset. Because if you were to just sort of go up and look here, there's no way you could have x being 12 because on this side you would have 16 minus 2 times 12. Well, that would give you a side length of negative, 32 or something. And you obviously couldn't have a side length of negative 32. And this one would be negative up here as well, right? It would be like negative 18. So you can't have side lengths of negative 32 and negative 18. So you could actually rule this one out just by plugging it in. 10/3, however, does work because we would get 16 minus 2 times 10/3. That would be a positive number. Be 20/3, so 12/3 or so each side. So we were just asked to find what size we would have to cut out, and that would be 10/3 of an inch. We would need to cut out the x's of 10/3 of an inch. Okay? And that would give us the largest volume. All right. You do not have a similar one to this one, but I wanted you to at least see one like that because it is possible you might see like something like that on the AP